Hi, my name is Prabhleen, and I'm a senior at Kansas State University, currently majoring in chemistry and biochemistry, and I'm working in Dr. Patricia Cavill's lab at the Department of Chemistry, and today I'll be talking about ABA triblock copolymers for water purification membranes. We know that there's various sources of water pollution in the world, such as agriculture, industries, etc., and one common thing about these pollutants is that they end up in water bodies like that of oceans, groundwater, etc., which leaves over 40% of the world's water bodies severely polluted. It is estimated that 2 million tons of waste are released into the water bodies around the world, and we know that these numbers are only going to increase because of rapid industrialization and population growth. So we need to find a way to make this water pure for human use, and membranes have been a promising strategy for water purification, especially polymer-based membranes whose physical and chemical properties can be changed, which can help in changing membrane morphology and also help in the selective filtration of water. For the purposes of this project, we're mainly going to be focusing on triblock copolymers, which are synthesized in two simple steps. The first is the formation of the macro-CTA by polymerizing monomer unit A in the presence of a chain transfer agent. We then take this macro-CTA to step 2 and polymerize monomer unit B on both sides of the macro-CTA to form a triblock copolymer ABA, which is a long polymer chain consisting of 3 distinct blocks. These studies have been conducted before where ABA triblock copolymers have been synthesized via RAFT, and the triblock copolymers, when put in the presence of DMF and water, which are common solvents, form flour-like micelles. The polymers were then converted to membranes by evaporating the solvents and by spin coating these membranes on silicon wafers. The spaces between these micelles are what were the pores, and the porosity of the film surface was estimated to be 44%. The pore size can be controlled by changing the polymer properties, and such membranes have potential applications in ultrafiltration and selective ion separation. For this project, we're mainly focusing on ways to synthesize these ABA triblock copolymers more efficiently, because their synthesis can sometimes be difficult due to larger molecular weight or larger chain length. And so we use both thermal RAFT and photointerferometer polymerization because they give us good control over molecular weight. But we also hypothesize that the photointerferometer polymerization, since it doesn't require an initiator, would give us better end group fidelity, which would help in the chain extension and would also give us lower dispersities. These are some of the steps that we follow in lab. We first prepare the reaction vial, which is then put either on a hot plate for thermal RAFT, or it is put under UV light for photointerferometer polymerization. The polymer is then precipitated or purified in the presence of a suitable solvent, and then we conduct nuclear magnetic resonance spectroscopy to find the percent conversion, or to see how much monomer has been converted to polymer, and then we can conduct SEC or size exclusion chromatography to find the molecular weight of the polymer as well as the dispersity, which is a measure of how uniform the polymer chains are, and this value should be close to 1. These are some of the monomers that we have used. For our macro-CTA, we have used a hydrophobic monomer styrene, and we have chain extended it with hydrophilic monomers listed here. The reason why we've used both hydrophobic and hydrophilic monomers is so that our final triblock can have an epiphilic nature, that is a dual nature of both hydrophobic and hydrophilic. So these are some of the results. We first polymerized styrene to form our macro-CTA. We tried various methods, both thermally and through photointerferometer polymerization, and we found out that blue light with acid was the most efficient because it gave us the fastest conversion in the least amount of time, and also the dispersity was 1.2, which is pretty close to 1, which says that most of the polymer chains were very uniform. We then chain extended the macro-CTA with various monomers, both thermally and via UV light. And one thing I'd like to point out here, that as per our hypotheses, the UV light did end up giving us higher molecular weights and also maintained a lower dispersity, which gave us good control over the molecular weight. And this is clearly seen in the SEC graphs because there is a clear separation between the macro-CTA as well as the chain extended polymer, and the graph shifting to the left just says that the triblock copolymer has been formed and has higher molecular weight. So in conclusion, we have synthesized a hydrophobic macro-CTA, and it has been chain extended with 4 different hydrophilic monomers through both thermal RAFT and photointerferometer polymerization. And as per our hypotheses, the photointerferometer polymerization did give us better control over molecular weight and as well as higher molecular weight. So for future work, we'd like to synthesize polymers with more CTAs, and also by using more monomers that have different hydrophobic and hydrophilic nature. We like to characterize these polymers using different methods and to understand the self-assembly and the micelle and pore forming ability of these polymers for membrane development. So I'd like to thank the Kansas Water Institute for funding this project, my PI, Dr. Patricia Calvo, and the chemistry department for giving me this opportunity to conduct undergraduate research. Thank you.